Hi, welcome to everyone. My name is Sanchez. I'm from Argentina, and I'm here to talk a little bit about my research work. In this particular case, we're going to talk about clays, carbonaceous materials, and magnetic nanoparticles confined in polyvinyl alcohol cryogels. As we all know, pollutants are present in air, in soil, and water. Among the most commonly found pollutants, we can cite dyes, agrochemicals, metals, and some other emerging pollutants. And it is important to say that some air pollutants and soil pollutants are found in water bodies, so achieving its remediation is of high importance. Among these pollutants, it is cadmium, that it is affecting human health through drinking water and bioaccumulation. And one of the most important consequences of the cadmium exposure is the generation of human cancers. So the World Health Organization has established a maximum concentration for cadmium levels in drinking water. As all of us know, the dose makes the poison. So let's talk about methodologies. Which kind of methodologies can we apply to remediate water bodies? So there are physical, chemical, and biological ones. All of them have certain advantages and disadvantages. And one of them mostly applied is the physical, because physical methodologies are commonly low cost, easy to be applied, and the main advantage is related to the fact that they do not generate secondary products as a result of the water treatment. What about the techniques? Well, they can be in situ or ex situ. The in situ techniques implies to apply certain water treatment in the place that is the polluted water body. And in the case of the ex situ technique, you have to remove water samples to treat them in some other place. Well, adsorbents is one of the physical methodologies that are mostly applied. And absorbents to conduct this kind of remediation have to be relatively cheap and readily available. They should have a high selectivity for the specific pollutants, and they have to be easy to be recovered from filters after the water treatment. They should be regenerable, and of course, we are looking for some non-toxic materials. Among the factors that are affecting the performance of polymeric materials as adsorbents, we can cite some inner from the type of polymer and some other that have to be with the physicochemical characteristics of the specific polymer. Now let's talk of hydrogel as absorbents. These kind of materials are usually applied in the form of films or beads, and they are applied into a water sample to conduct a water treatment, and after a certain amount of time, we have the pollutant inside the adsorbent. As we can see here, we have a hydrogel having methylene blue inside it, and it is common that this kind of materials could be reused. So hydrogels are cross-linked three-dimensional polymer networks, and that usually have hydrophilic groups that impart to the material high swelling capacities, and they can be cross-linked through two methodologies. The first one, the chemical, and the second one, the physical one. Through chemical cross-linking, we generate covalent unions, whereas when we apply physical cross-linking methodologies, we are generating ionic or hydrogen bonding unions. One of the most commonly employed materials to generate hydrogels is the polyvinyl alcohol, or PVA. And we can find this material in different polymer weights, and also with different hydrolyzation degrees. Among the most outstanding characteristics of the PVA, we can cite their biocompatibility. They are hydrophilic, they are relatively inert, and they are eco-friendly. And it's very important to say that PVA can be cross-linked through a physical cross-linking method consisting in different freezing and thawing cycles. So we have a PVA solution that is freezed to generate PVA chains and ice crystals. And then when we thaw this system, we have PVA cross-linked chains and pores. And in this way, we generate a PVA cryogel. So let's talk about nanomaterials. They are materials having very, very tiny sizes, and they are having specific properties that are notably different when they are compared to the corresponding bulk materials. So the possibility to conveniently design the size, the shape, the characteristics and properties of the nanoscale devices makes nanotechnology a very useful tool. Although nanomaterials have proved to be very useful for water treatments because they have high selectivity and high activity as pollutants removers, there are two topics that should be considered. The first one, when we use nanomaterials, they are not easy to be recovered after the water treatment. And the second one is that there is not much knowledge about the potential damages or disadvantages on the employment of nanoscale devices. So we have to be careful until more knowledge is should be found, you know. So to fix these disadvantages, we can generate nanocomposites. When we generate a nanocomposite, we confine certain materials that are active for the specific topic that we are looking for, and we put them into a matrix, for example, a polymeric matrix. In this case, we have easily recovered recovering materials, and they usually offer better treatment times, higher absorption capacity, and better life cycles because they can be easily removed and reused. Nanocomposites usually have excellent potential as highly efficient water and waste treatment agents. And of course, we can tune the materials in order to have relative low-cost preparation procedures. So, taking all of this in account, we have two main general objectives. The first one, to develop and characterize composite PVA-based hydrogels with fillers of different physical and chemical nature. In this case, we employ clays, iron oxides, and carbonaceous materials. And of course, we look for evaluate the potential of these materials as absorbents for cadmium removal from water. So let's talk about materials and methodology. As a starting materials, we use polyvinyl alcohol from Eldridge, natural bentonite, acid-modified bentonite, magnetic nanoparticles, and starch-derived mesoporous carbonaceous materials. All the last three materials were prepared by ourselves in our laboratories with the procedures that we have developed, and they are already reported in papers. So, regarding the methodology, firstly, we have to prepare a PVA solution by heating and stirring it, and then once the solution is prepared, we incorporate different amounts of magnetic nanoparticles or carbonaceous materials, keeping this constant stirring to generate a suspension. In the case of using clays as a sorting material, we firstly have to swell the clay overnight at room temperature. And once this step is completed, we incorporate to this suspension different one polyvinyl alcohol to the system. So we have different suspensions, 4 of them, and we cast into anti-Hadrian molds, and then we cross-link the different materials through the physical methodology that we have previously described. So in this way, we have prepared 1 neat PVA hydrogel that was acting as blank, and 11 composite hydrogel samples with filler contents from 1 to 5 weight %. All of these samples were characterized through Xray diffraction, scanning electron microscopy, 20-degree diffraction determinations, thermographic analysis, scanning differential, scanning calorimetric measurements, and we finally conduct some cadmium removal efficiency tests. Let's start with the Xray diffraction. We can see in the first graph, the bentonite containing composite hydrogels do not have the bentonite peak. So this is an indication that we have exfoliated clays within the PVA matrix. In the case of acid-treated bentonite, we have this bentonite peak, but it is present in lower angle values. So we can say that the PVA chains are integrated into the clay structure. And then we finally have the Xray diffraction plot for the magnetic nanoparticle containing materials. And we can see the peaks corresponding to an iron oxide mixture. In all cases, we observe the semi-crystalline peak of PVA near to 20 degrees. Then we saw the pores, the morphology of the different hydrogels through the analysis of SEM micrographs. In here we have a neat PVA hydrogel having very porous structure. Then in here we have the bentonite containing materials. We can see that we have larger pores, but they are not well distributed. In here we have the acid-treated bentonite containing materials. We can see that we have well-defined pores, well distributed among all the samples. In here, we have the magnetic nanoparticle containing materials. We can see that in here, we also have well-established pores and a good distribution of them. And finally, we have these carbonaceous materials containing composite hydrogels. We have larger pores, but they are not well distributed. So we explored some of the factors that usually affect composite hydrogels morphology, and we proposed this model that is already reported in some papers, in which we established the way in that the pores are formed in the composite PVA hydrogel. So we have the PVA rich and poor phases, we have amorphous and crystallized of PVA, and we have the most important thing is that we can have some hydrogen bonding interaction between the filler and the PVA chain. The materials that we have employed in here that could most interact through hydrogen bonding with the PVA are the magnetic nanoparticles and the acid-treated bentonite. And in both cases, we saw that they offer well-defined pores and a more well-distributed pores morphology. So this is our hypothesis. Then in here we have the 7-degree measurements, and in almost all cases we can see that the neat PVA hydrogels offer higher swelling values than the composite hydrogels, and when we increase the filler contents in the composites, the swelling degree decreases. This behavior was observed in almost all samples except with the magnetic nanoparticle ones, and we think that this behavior is different in this case because we have some agglomeration of the employed filler. In here, we are presented the hydrofraction dependence on filler content of the composite hydrogel, and we can see that in almost all cases, the hydrofraction remains constant or slightly increases when the filler content. This increase in the hydrofraction with the filler content could be attributed to the fact that the filler could act as a cross-linking dot, and this is well reported in different papers. So in here we are looking for the relationship between the swelling degree and the hydrofraction of the different materials that we prepare, and we can see that when the hydrofraction increases, the swelling degree decreases. This is a result of this fact that the fillers can act as cross-linking dots. And it is important to remark that the higher swelling values were offered by the samples that contain the bentonite, and this could be attributed to the fact that this is the filler with the most affinity to water. Here we have the different differential scanning calorimetric measurements, and we can see that in almost all cases we have a double glass transition temperatures, which is quite common in PVA hydrogels. And in all cases, the glass transition temperature values are slightly increases with the filler incorporation, and this can be explained in terms of the PVA change mobility. When we have a wood filler PVA interaction and higher filler contents, the PVA change mobility is reduced, and this is the effect in the thermal properties. Finally, we test the cadmium removal capacities of the different materials that we prepare. And in all cases, we can see that the PVA matrix has a really bad ability to remove this pollutant, but the addition of the different fillers has improved the material's ability to remove this particular pollutant. In almost all cases, when we increase the filler content, the capacity to remove the pollutant was increased too. And this behavior was independent on the filler's nature. So in summary, pollutant absorption using a polymeric hydrogel is a complex process that depends on its surface area, pore size, distribution and structure, cross-linking degree, diffusion capacity, and on its specific chemical composition, since the pollutant can interact with the absorbent through electrostatic attraction and or complexes formation, for example. Conclusions. PVA composite hydrogel containing natural and modified bentonite, magnetic nanoparticles, and mesoporous carbonaceous particles derived from starch with filler loadings from 1 to 5 weight % have been prepared, characterized, and tested for cadmium absorption. It was found that each filler imparts to the hydrogel a defined morphology for size, swelling degree, hydrofraction, and thermal properties. In general, with filler addition, the swelling degree decreased, while the thermal stability of the materials increased. SEM of the samples demonstrated that the pore walls of the PVA acid-resist bentonite and magnetic nanoparticles were thicker, and they also have a more regular pore structure. The employed fillers can interact with the PVA through hydrogen bonding and stabilize the hydrogen structure better via the widely accepted three-phase model when describing the freezing thawing prepared PVA hydrogels. It was also found that all composite hydrogels displayed in HIMSS cadmium absorption capacities compared to the neat PVA hydrogel, and a clear correlation between the filler loading and the absorption capability was found. Considering the fossil preparation procedure, the steerable structural properties, and improved absorption capacity, it can be assumed that the obtained results are promising and that the developed materials could be tested for the remediation of other problematic heavy metals such as chrome, lead, and another important pollutant like arsenic. In here, I'm showing you the paper in which most of these results are reported, and in my email, just in case one of you want to talk more about this kind of results or some other composite materials. We thank all the financial support from different agencies, and I want to thank you all for your precious time. And special thanks to the organizing committee to inviting me to be part of this webinar. So once again, thank you all and have a nice day.